Afternoon, everyone. Welcome to the track. I'm going to jump straight into this so that we remain on time. Christopher Neugebauer is an Australian developer, speaker, and serial community conference organizer who presently lives in the United States. He serves as a director of the Python Software Foundation. He's a co-organizer of the acclaimed North Bay Python Conference, a statement he wrote himself, a boutique one-track conference run in unusual venues, including an old theatre and more recently a barn on a farm. Christopher is also a contributor on the open source Pants build system, helping make Python's testing, correctness, and style tools accessible and fast for developers, no matter how big their code base. Chris's talk is Let's Make a Working Implementation of Async Functions in Python 2.1. Also, why you might want to use a more recent version of Python. Take it away, Chris.
Hey, thanks, Nick. Hello. How are we doing here? Can we hear me? Excellent. Okay, so as Nick mentioned, my name is Christopher Neugebauer. And before I begin, I do need to issue a slight apology because regrettably, I am not going to be able to present the talk that I advertised in the program. I was unable to get Python 2.1 installed on my Mac this week. So today we're going to be talking about how to make a working implementation of async functions in Python 1.6 and why you might want to use a more recent version of Python. So I'm in a lot of places. You may know me from my work with the Python Software Foundation or on the North Bay Python Conference. It's in April next year in California. Come along if you're able. But what's important is that I've been around this community for a while, and I care a lot about the health of our community. And being in this community, I hear often things like, Python isn't for me anymore, or Python is just too complex these days. And it's very easy to agree. There are so many new things in Python, so many things. Look at all of them. How can you remember all these things? And you might ask yourself, why do we even need all that stuff anyway? So yeah, I came for a language 20 years ago, and I liked that language 20 years ago a lot. And I've stuck around, and it's easy to get annoyed. There is a new Python every year, and with new things to learn. And C programmers don't have to learn a new language every year, so why should I have to? So today, I'm here to extend an olive branch. You do not need to learn new versions of Python every year to get the more useful things that we work with today in modern versions of Python. So today, we're going to talk about async functions. So async functions are how we scale I/O-bound applications in modern Python. So first up, let's answer the question, what is an async function? Async functions are what Python calls, what computer scientists call coroutines, which are units of code that can have their state suspended so that you can stop execution, hand off execution to another context, and resume execution later. Async functions can communicate bidirectionally. They can send data out, but they can also take data back in. And importantly for us, async functions are suitable for use in an event loop. Event loops allow for things to happen outside of the context of our coroutines and to communicate when those things happen back to the coroutines that care about those things happening. So we are going to try and write some async functions here. We need for them to be suspendable. We need them to have state that is suitable for storing in an event loop. And we're going to work with the syntax that we already have in Python 1.6. We are not going to actually write the event loop or any async IO functions because this is Python 1.6, and around the time of Python 1.6, Twisted was getting started, and they're going to solve that problem for us. So we just need to give them a programming construct that they can actually use. So Python 1.6. There is a lot of language there in Python 1.6 that we don't have these days. It was such a simple language. It was so simple that it was missing things like true and false. It's missing things like iterators, let alone generators. It's missing real scoping rules. And most importantly, it's missing yield. And not having yield is really important. Yield is what gives us suspendable functions in modern Python. So we're going to have to do some real work here. And that real work, we're going to begin at Python 3.5. And Python 3.5 is notable because it is when async and await were basically fully formed. And we're going to work backwards because not a lot of Node has happened since 3.5. So quick recap for those of you who don't know. Here's what async and await looks like in modern Python. So you can spot an async function in Python because it begins with this word async. This is really important because having async at the start of your function stops you from awaiting things that aren't async. And this async function here actually doesn't do anything asynchronously. But if we add this async io.sleep thing, suddenly we're allowing our function to suspend for a few seconds and then get reactivated by something. And that something is the event loop. So what happens when you await a coroutine is that the coroutine may eventually return a future, which is an object that indicates when some event has occurred that some other coroutine is depending upon. And when that future is ready, the result of the future gets handed back to the coroutine and it continues along its way. But async IO actually appeared before async and await were part of the language. They were there in Python 3.4 because there was a feature that showed up in Python 3.3. And that feature is called yield from or generated delegation. So the idea of yield from is that if you have a generator coroutine that calls another generator, you used to have to loop over that generator to yield all of its contents. But with yield from, you can just say yield from the generator that you want to delegate to. It's one line of code. It's very, very simple now. You may be asking yourself why this is important and wondering like what value is there in just transmitting all the values from one iterator to another without doing anything in between. But a lot of use cases for coroutines, even at Python 3.3 time, were built around doing async IO, even before Python started doing it in their core development work. And once you're doing that, the for loop approach doesn't make a whole lot of sense. So here's our modern async and await approach. It's really clear to us what's going on. We're saying await the sleepy thing. But let's see what we had before yield from came around. We need to use a for loop and iterate over it. And this is not too bad if you're not planning on making use of the value that comes out of the coroutine that you're delegating to. But if you do need that value, things start to get awkward. Even if you know that only one value is going to come out of that delegated function here, you still need a for loop. If you know there's only going to be one value being yielded, then sure, you can sort of use the iterator protocol directly. But that's a code smell. You don't say, I'm going to iterate over this and treat this as an iterator just for one thing. That doesn't make a whole lot of sense. But with yield from, you can kind of sort of suspend the disbelief that there's iteration going on here. Async await, it's definitely better as a construct, but this is something that we can work with. So if we want async in older versions of Python, we're going to need to re-implement generator delegation. And here's the basis of that. We're going to create a class called from, which is going to accept an iterable, and it's going to store the iterator that we get out of that iterable. And from this class itself will implement the iterator protocol. And basically what this does is maintain a call stack of delegated generators. It asks the iterator at the top of the stack for an item, and if we see a from object come out of that iterator, we know that we're going to need to start yielding from that from, and so we're going to push that to the top of the stack. And we keep iterating through that until we've exhausted everything. And finally, we need a way to handle the froms that come out of that top level generator, which this decorator here is going to solve for us. So here is a yield from generator that works in Python 3.3. And here's the same setup that will work in Pythons as old as Python 2.2. It doesn't look very different. That's great. And so with this custom implementation of yield from, we have the tools that will let us implement generated delegation. And it doesn't take a huge leap of faith to rename our from wrapper to, I don't know, await, and that delegates decorator to async, but we didn't do that here. And more importantly, this is going to cover every version of Python all the way back to Python 2.5 as far as features go. And that came out around 2006. So the next thing we need to deal with is bidirectional communication, and that's this equals yield syntax. This was added around Python 2.5. And these are a feature that I'm going to call channels. They let us send things back into a running coroutine. So when you're working with an event loop, this basically provides us with a way to yield out a future and then resume our coroutine once the result of the future is added back into the coroutine. And this was useful in the development of async functions because before channels were there, you could really only communicate things outwardly. And that's not so hard to work around. Because in Python, everything is an object, and more importantly, we as programmers can create our own objects. And so here is such a class that makes such an object. It's going to call it coroutine, and it has a thing called slot and a thing called instance. And it implements the generator channel protocols send and throw. And it's also still able to act as an iterator because that's important. The only thing that our iterator needs to implement here is the body. And so here's a quick implementation of a guessing game that uses native yield expressions. It works in Python 2.5. And then here's the version that uses our hard-coded yield expression type channels. It's very simple, similar. You have to implement the coroutine as a method of a subclass of a thing, and you need two separate lines of code to do the communication. One to send data out, and one to read the slot's value back in. This is relatively simple, right? And this is going to work in every version of Python going back to Python 2.2, which is as long as we've had native generators in Python. So now we have backfills for two features that let us implement full bidirectional communicating coroutines with automatic delegation. And so that leaves us with one feature to implement. And that feature is yield. So yield came around in Python 2.2. And that's what enables suspending functions at all in Python. So surely we need to have that to make this work. So one thing about Python is that it is a bytecode interpreted language. And it has been for a while. In fact, it has been for basically as long as Python's been around. Just checking to see if anybody who knows could nod for me. Yeah, thanks. So here's a short function in Python. It doesn't do anything interesting at all. But one good thing about this function here is that it is short. And that's going to be really important in a moment. And it uses so little Python that it works in Python 1.6, which is also very useful for us. Because I got Python 1.6 running on my actual Mac. It's running on my actual Mac right now. You can install it using conda if you want to try it out yourself. Just go conda install Python 1.6. And this is the thing that Python has had for a very long time, is the disassembler module, or dis. And dis is useful because it can show you the bytecode that a Python function gets compiled to. So let's take a look at what our disassembled really short function looks like so we can see what comes out of the disassembler module. You can see that there's a bunch of opcodes and offsets. And in this right column here, it tells you exactly which bit of code corresponds to the bytecode operations and the operands in that. So here's our function. And you can see that this block of bytecode here corresponds to the if clause in your Python source. But there's some other cool things in this as well. There's jump forward, which takes an argument, which is a number in this case, and that's how many instructions in the bytecode object to jump forward by. And then there's also set line no, which cleverly tells us exactly which block of bytecode corresponds to which line of our original Python source code. So if we wanted to suspend a function, if we knew exactly which line of code we were suspending at, we would know exactly where into the bytecode to jump and to resume it at the next line of code. I told you that at the start. Pay attention. This is where sys.setTrace comes in. So sys.setTrace is a function in CPython that lets you trace the execution of code. It's there so that you can write a debugger for your Python. But where's the fun in that? sys.setTrace can trace a bunch of things. It can trace when you call a function. It can trace exception handling. It can trace the execution of individual lines and of specific function return calls. So trace function, it takes 3 arguments, and from right to left, there is the magic argument that we don't care about. There is the event, which is a string, which tells us what sort of event we're going to be handling here. And then there's the frame, which gives us all manner of information about what we're actually tracing. So we're going to look inside this frame object, and us as modern Python programmers, we'd go help frame and get all the help for the frame. This is Python 1.6, we don't have that. But we do have dir, so we can at least see what attributes are on the thing and then poke around at the object ourselves. So there's things like f_back, which gives you the previous stack frame so that you can sort of unwind and do a stack trace if you wanted to. There's locals and there's globals, and these are the local and global variables that are in context at the time the trace happens. There is f_code, which is the code object that's being executed. And then there's f_line_no. And this corresponds to the number of the line that is being executed at the time the trace gets called. So now we have everything that we need. Great. We're going to create a class called suspendable. It can track a bunch of things, such as the mode the coroutine is in. That's just a state machine that we'll see in a moment that tracks whether we are yielding, whether we are restoring from a suspended state, whether we're stopping iteration. There is a method called yield, which puts our suspendable into yield mode. And there is next, which we're going to talk about in a moment. So now the only thing that's left for the implementer to do is override the body method, which is pretty easy. You can do that. So here is our trace function. Our trace function has 2 parts to it. For call events, this is when a function is getting called into. We're going to say that this tracer will only run on a function that is called body and whose self-param is a suspendable, so that our trace only does weird things to suspendable objects. And then if we're calling return, we're going to do different things based on whether we are in yield mode or not. If we're in yield mode, we're going to save the stack frame for later use, and then we're going to enter restore mode so that when you call into the coroutine the next time, it's going to restore it. And here is the next method. If the coroutine is stopped, we need to raise stop iteration. And stop iteration is actually an exception that I wrote because in Python 1.6, iteration didn't exist. So of course, stop iteration didn't exist either. But if we're not in restore mode, we're going to start running the body function. If we are in restore mode, we're going to unsuspend our suspended function. And here's the implementation of our unsuspending code. It's very short. It's less than 15 lines of Python. So here's the code that is going to look for the bytecode instruction that corresponds to the line of code after the one where we suspended. And it's going to produce a new piece of bytecode that starts by immediately jumping to that instruction. Okay. Here's the code that makes a new code object with our patched bytecode. A fun fact that I discovered when writing this is that there's no way to construct a code object in Python 1.6 except by taking a serialized code object and running it through Marshall. Don't ever use Marshall. And here's the code that replaces the code object for our body method. It's going to run that updated code, and then it's going to put the original code back so that people who are inspecting things couldn't see what happened. And that's all you need to do. And here's what a coroutine looks like for Python 1.6. You'll note that I haven't made local variables work, so you need to put all of your values on self at the moment. I don't think that putting local variables in here would be a particularly hard lift because you get all the local variables in sys.setTrace. It's just that doing that would be another 30 lines of code at least, and that wouldn't fit on a slide. And where's the fun of a demo that doesn't fit on an entire slide? And this does actually work. You can store stuff in self, and it will be there as state, and your code will start executing in the middle of the loop. And so that works in Python 1.6, which gets you all the way back to the year 2000. And let's be extremely clear, there was probably one person in the world who could have seen the value of suspendable coroutines for asynchronous I/O back in 2000. But I'm pretty certain this code would have worked earlier. The overall techniques here, they work all the way up to Python 3.11, which is when they started adding in optimizations into the bytecode interpreter, and it became far less easy to figure out what was going on. But it will work back to Python 1.0 as well with some minor modifications. And so that's it. It is clear that there is no reason why we need all that extra language that's been developed over the last 25 years. Okay, but clearly that's not true. I use Python 3.12 in my day job. You probably use Python 2. Probably. I hope you're not still on 2.7. Hey, but what? Exactly. That was around when Anthony was still releasing things. The language did have everything we needed before I started using Python. But Python grows incrementally. Python 1.6 was a small leap from Python 1.5. All Python 1.6 really did was add Unicode strings. Python 2.0 was a small leap from Python 1.6. And Python 2.2's generators were a small leap to make it easier to iterate over data structures. They weren't written to make async I/O an easy thing to do. Coroutines were genuinely weird back in 2003. In 2005, I read Knuth for the first time, and I saw that he'd been pushing this idea of coroutines since the 1970s as something that should be really useful. But between him writing that, most languages just decided it was far more complicated to do coroutines, and you should just use threads, even though we know these days there's all manner of trade-offs using threads. People just did not care about coroutines. But what did happen is that iterators started happening, and generators existed to make iteration easier. This is an iterator in Python in 2.1 and earlier. Basically, you had to implement get item with an index and pretend that you were a list. And that's really silly. So Python 2.2 introduced iterators, but writing iterators was actually quite complicated. So we got generators at literally the same time. Generators make writing iterators easier. And once we got iterators, Python started using iterators everywhere. You could argue that we got Django's streaming ORM entirely as a result of iterators existing in Python. And by Python 2.5, the try-finally construct had been around for a while, and people saw its limitations. So Python started investigating context managers. Context managers, like iterators, had a protocol that you could implement inside a class. But like iterators, the protocol is really difficult to handle manually. And this was something where the state suspending features of a generator could have been really handy, but you needed to be able to send an exception back into the generator in order to do cleanup and error handling properly. So this was a great use of the coroutine. And so context managers and the yield expression that made them easy to use literally got added to Python within 3 days of each other. And at this point, Python had its basic coroutines, and we started on this 10-year journey towards async and await. Now, I'd say that by Python 2.5, async with coroutines was an inevitability. Twisted was playing around with it a bit, but it still took a while for core Python to really take things seriously here. And the last 2 steps got us to where we are today. We got yield from, which made it clear that delegating to other generators was something that you might actually want to do. And the first version of async I/O was actually written entirely around yield from, but it was still really hard to understand, like why are you going yield? So async and await made it easy to read code and understand how async functions interacted with each other. And in particular, it prevents you from awaiting a non-async function. The syntax guides you in how to use it, which is to say, it wasn't really until Python 3.5 came along that it was really obvious how to use coroutines for tools other than iteration, even if you could theoretically have written them back in the earliest versions of Python. And this is because Python and Python developers value constructs, which is to say that Python as a language shapes how you write your code. It provides you with a limited set of tools, and you work with those tools to write your code. So I've just seen that you can write very reasonable looking async functions in any version of the language that supports generators, And in fact, you don't even need generators at all, since you can patch Python bytecode and write your own coroutines in old versions of Python. Okay, but you don't do that, do you? And you don't do that because it's weird. Good production standard Python does not value doing weird things. In Python, we believe that syntax conveys intent. You use a particular piece of Python, the language, because as well as doing the thing that you want, it conveys to other people that you are doing the thing that you intend to do. And one result of this is that new features of Python are very rarely groundbreaking. New features are ones that very slightly dent the boundaries of what's possible or what's reasonable to accomplish with the language. So when I started writing this talk, giving this talk, I promised a working version of async functions for people stuck on Python 1.6. Oh, lights. That's exciting. Wow, there's a lot of you here. I promised a working version of async functions for people stuck on Python 1.6, but I also asked why you might want to use a more recent version of Python. And the answer to that question is that newer Python already has all this stuff, and people might understand what you're doing. Thank you very much. I'll take some questions if we've got them.
We've got some time for questions.
There's Tom over there, and then there's Anthony.
We have your last slide up, please. You mentioning the opcodes kind of made me curious. Did they evolve a huge amount over the years as well, and specifically to implement these features? As a follow-up question, like how were they actually implemented in real life?
Yeah, there was changes made to the VM and what the VM could let you accomplish. There's all manner of new things in the Python bytecode spec that have appeared. A lot of things around actually doing looping in a particularly useful fashion, but also opcodes to suspend execution so that you don't have to do all of this. But yeah, another thing that I mentioned was that around Python 3.11, the techniques that I was doing wouldn't really apply. They added a lot of things around performance optimization as part of the faster CPython project that happened. So doing this in Python 3.11 would be a lot harder, but also you have yield in Python 3.11, so you really wouldn't want to.
Your
Yes.
code makes copious use of set line no. Isn't that just goto?
So setLine no is not actually goto. Setline no is it's basically a comment inside the bytecode that's saying this is the line where the bytecode interpreter is executing at the moment, so that when you make an error, it will print out the source code and say what line number your error happened on. They stopped using that particular opcode sometime in the Python 2 series, at which point it became a lot harder to do that particular thing. This is not a lightning talk. Cool. I'll be around for the next 10 or so minutes at least. Happy to take any more questions or arguments from people. Thank you all for coming along.
Thank you very much, Chris. As a token of our appreciation for bringing such a fantastic talk to PyCon AU, we present you with this year's mug, which we hope you can get home on a plane.
I've succeeded in the past. Thank you very much.